Hi, and welcome to the Harmony Strategic Simulator presentation. This presentation will first of all cover an introduction of the Harmony strategic level, followed by a few details about the architecture of the strategic simulator, and finally an overview of the models and components that are part of the strategic simulator. On the left-hand side of this slide, you can see the architecture of the Harmony MS structured over three different levels. The first of which is the strategic, which is a simulator composed of an integrated suite of aggregate and disaggregate land use, socio-demographic, regional economic, and long-term logistic choices model. Downstream to this, we have the tactical level, which is an agent-based transportation demand and supply modeling framework composed of two main submodels, a passenger and a freight simulator. And finally, downstream, there is the operational simulator, which is an integrated demand and supply simulator operating at a shorter term. The strategic simulator is composed by different models or components, and they are a regional economy model, a land use transport interaction model, a demographic forecasting model, a land development model, a spatial interaction freight model, a firm synthesizer, a vehicle stock model, a long-term households and individual choices model, and a synthetic population model. The idea is that the strategic simulator is not a black box providing results by default. Rather, it should be seen as a toolbox whose models are the tools that can be chosen or assembled together according to the user's modeling needs. We will now take a closer look to the strategic simulator architecture. Here we can see the data flow among the different strategic components, as the idea is that the outputs of a model can be the inputs of another. The models interact among each other and with exogenous sources or other models within the Harmony MS at different levels. Different models can be combined in different templates, and according to which models are selected and coupled and integrated among each other, the data flow here presented will evolve accordingly. We will now proceed to an overview of the different models with the idea of providing a general understanding of what they are, what they do, and how they can be combined together. This presentation will cover the first 6 components of the strategic simulator, which are the ones highlighted in this slide, as the last 3 are closely related to the tactical simulator and will be presented together with the tactical level. The strategic models have been applied to the 4 Harmony case studies that are Oxfordshire, Athens, Rotterdam, and Turin. And in the next few slides, you will see a few examples of results and applications. However, these models are designed to be flexible and adaptable also to other case studies. So the first strategic model that we are going to present is a demographic forecasting model whose main scope is to address the need of an accurate idea of how and where the population is going to develop. The demographic forecasting model provides a framework of models, different models for the estimation of population of both people and households at a high level of spatial resolution. For UK case studies, we use the Spencer framework, which is a synthetic population estimation and scenario projection model. It's an open model developed by University of Leeds, and our job here in Harmony was to make it work in combination with the other Harmony components. But since Spencer is very UK specific and it requires a high level of precision in terms of input data, we also developed a DFM demographic forecasting model Lite for other applications. Here we can see the architecture of the Spencer model, which is structured over 4 different phases. And in the top part of the slide, we can see the theoretical framework, and below the correspondent software implementation of all these 4 phases. First of all, we have a data retrieval phase, and Spencer does it with a few Python libraries called UK Census API and UK Population. Then phase 2 consists in the creation of synthetic population of both people and households. Then we pass to the projection of this population in time and also the assignments of people to households. And finally, phase 4 is the output phase.
The demographic forecasting model light version has been designed and developed in order to be applied in those contexts where there is a limited amount of data availability. The objective is therefore to estimate the evolution of population and households with basic equations, applying yearly growth rates. Those are exogenous provided to the model. The growth rate of the variable is applied to the value of the previous year in order to project the evolution over time. More in detail, the equation for the estimation of population is segmented by zone, age, and gender, while for households, it is segmented by zone and number of components. Common data sources which could be used for the application of the model are Eurostat, National Regional Statistics Database, EU or national demographic projections. At the bottom of the slide, you can see some example of the outputs of the model which has been applied for Turin. On the left, the age distribution by gender in 2019 and 2030, and on the right, a map representing population density. The DFM Light model is used to estimate population and household trend and feeds the other socioeconomic models of the strategic level. First of all, the regional economy model. The objective of the model is to estimate the trend of employment by economic sector in the study area based on both national and regional factors. The national context is considered to represent on one hand internal features and on the other hand international competitiveness. Both these aspects are influencing the national economy trend and the interdependence with other regions. For the purpose of the model, these are taken as fully exogenous and not modeled endogenously in the regional economy model. More in details, the variables providing the national economy trend are the national GDP and the corresponding trend of sector employment, which is highlighted in the first part of the general equation reported below. The other factors influencing the trend of employment are related to the regional context of the application. More in detail, the model takes into account transport investments, tourism, population, and income. These are highlighted in the second part of the general equation reported below. Both the regional and national growth factor influence the regional growth, taking into account also intersectoral interactions. As a final step, to provide the output at zone level, an exogenous distribution of jobs by sector by zone is applied. Here you can see some details related to the data segmentation and calibration of the regional economy model. The model accounts for 24 economic sectors defined as aggregation of two-digit nomenclature of economic activities classification. 8 exogenous trend variables are influencing directly the projections estimated by the model. As mentioned, those are related to both national and regional factors. Common data sources used to develop the application are database from Eurostat, OECD, World Bank, National Statistics, and EU projection scenarios. The intersector coefficients are related and derived from input-output matrices. And calibration parameters of the general equations are estimated in a twofold way. On one hand, an econometric estimation based on regional data at NUTS2 level taken from Eurostat database has been performed. And on the other hand, multiplicative parameters have been estimated to adapt the model to the specific characteristic of the regions. Finally, the jobs distribution by zone is estimated with exogenous shares, which could be modified to simulate relocation of economic activities. The model has been coded in Python and calibrated for the period 2012-2018. Overall, the model reproduced correctly trends and the relevance of economic sectors. Nevertheless, it is a partial equilibrium model, which is a stable model with smoother changes. Here you can see some examples of the outputs of the model applied for Turing. On the left, the job distribution by economic sector in 2019 and the changes estimated for 2030. And on the right, the trend of total employment with respect to GDP trend and the map representing job density in 2030.
The land use transport interaction model is actually a framework of models working in parallel. It's a classical spatial interaction model, a gravity model simulating 4 different daily activities. We have a journey to work, a journey to retail centers, journey to schools, and to hospitals. And the mathematical formulation of the model is presented in the right-hand side of the slide. What we want to evaluate here is the flows of people among different origins and destination within the different daily activities and by different modes of transport. So what we want to evaluate is Tijk. T is the flow of people, I are the origins, J the destination, and K the mode of transport. So we have our origins, I, where we have activities or attributes, EI. This could be, for instance, population at origins. And we also have our destination J. In this case, in this example, this could be workplaces. So we have people traveling from home to their workplaces. Workplaces will have an attribute, an attraction factor that we call AJ, that could be the number of jobs. So the higher the attraction factor, the higher the number of jobs at location J, the higher the probability that people living in location I will travel there for work. But we also have to consider distance. So the higher the distance or the higher the travel time, or more generally, the higher the travel cost, the CIJ, the lower the probability that people will travel from origin I to destination J. But we also know that in our cities, there are several available modes of transport. So you can travel using your car or public transport, and these will entail different costs. So we could have a CIJ1 for one mode of transport and a CIJ2 for another mode of transport. So combining all these different factors, we evaluate the flow Tijk between origins I and destination J by mode of transport K. However, we don't want to evaluate that only for a single destination. Rather, we would like to have this information, the flows of people traveling, to all the possible destinations. But actually, we want this for all the possible origins and all the possible destinations in our city systems. And this is what the equations on the right-hand side of the slides are about. And as mentioned before, we have applied this to the different harmony cities. This is, for instance, an example for the city of Turin, the functional urban area of the city of Turin in Italy, and we are plotting car flows and buses flows. While this is an example of another application in the city of Athens in Greece, and here we're plotting private transport flow and public transport flows. And finally, this is an example of the UK case study of Oxfordshire. And again, we're plotting car flows and buses flows. In addition to flows, land-use transport interaction models can also provide us with useful information about accessibility measures. And for instance, here I'm plotting housing accessibility and jobs accessibility in the different applications that we have seen before. We have Oxfordshire on the left-hand side, Athens on the top, and Turin below. The land development model consists in the combination of different GIS layers, translating physical and development features into constraints and mathematical functions to provide suitability and desirability indicators for residential land development. The idea here is to combine the different layers and overlap them, first of all rasterizing them and matching their geometries, and then translate that information into mathematical functions that could be either linear or Boolean according to whether the layers are representing constraints or accessibility or desirability indicators. Here we have a high-level workflow of the model, and the important thing to remember here is that we have positive attractors, negative attractors, and constraints all combined together into a single equation to provide the final results. The user can set up different scenarios using this model, switching on and off different layers, combining them with different weights according to their modeling needs. Here is an example of Oxfordshire, and for instance, in the below picture, we can see a ring, an empty ring around the city of Oxford, because in this case, we didn't allow residential development in the Greenbelt. And these are other examples of our application. We have Athens on top and Turin below, and we also are experimenting here with different scenarios. And for instance, in Turin, we can clearly see rivers, as we didn't allow residential development in high flood risk areas in this particular scenario. Finally, this slide is just to mention the different potential resolution that you can achieve with this model. Here in Turin is an example where we got down to the 10-meter resolution. Of course, there is a trade-off between precision and running time that the user needs to evaluate before setting up this parameter.
The firm synthesizer is implemented as part of the strategic freight simulator. And what it does is that it creates a firm population. So that's a data set of individual synthetic firms. And each of these firms will have their own identifier, sector, number of employees, and their location in the study area. The most important inputs for this module are the employment in every zone by sector, and a firm size distribution. And what this module does is it basically discretizes this zonal employment into individual firms. And these individual firms are then used in later modules of the Harmony MS, such as the tactical freight simulator. What's nice about having individual firms is that you can also model decisions later on at the level of individual firms, so that gives some more realism to the modeling. So instead of just modeling flows between zones, you actually have a firm deciding on, for example, a shipment size for one of their shipments. And also an advantage of having this module is that you can have a firm population for a forecast here. So if you have a forecast employment for the zones in your model, then this allows you to also have a firm population for the future year. So how this roughly works is that you loop over all the zones in your model, and you loop over the industry sectors in the zone. And for the employment for this zone and industry sector, you use Monte Carlo simulation to iteratively draw firms with a specific size until you have the full employment for this zone and sector. And afterwards, what we also do is within the zone, we assign every firm a specific location. So the firm will have coordinates placed somewhere within the zone. In this figure, you see the outputs of one run with the firm synthesizer. So every dot on the map here is a firm that is created and placed somewhere in the Rotterdam area of the Netherlands. What you can see here, for example, is that in the city center there's a notable concentration of retail firms, which are red here, and also in services in yellow. And on the figure on the right, it's zoomed in a bit to the city center of Rotterdam. So you see here that it's really individual firms placed somewhere in the city center. Besides the firm synthesizer, another submodule of the strategic freight simulator is the spatial interaction freight model. The purpose of this model is to disaggregate commodity flows at a more aggregate level towards a more disaggregate zoning level. In the Harmony project, for example, we took a commodity matrix from the Dutch national freight model Basgoed, which has a relatively aggregate zoning system, and disaggregated this towards a more detailed zoning system. And we've also used the European trust model for this purpose. So this module is flexible to different inputs. And another input this model uses is the employment in every zone by industry sector. And for this, for example, we can use the outputs of the regional economy submodel. So in this figure, you see a bit more how the module works. The module uses the regional employment to calculate the total commodity demand in every region. And then it uses the external commodity matrix as sort of the starting point for the output commodity matrix. And what we do then is to apply an iterative proportional fitting algorithm to make this commodity matrix fit with the calculated commodity demand by every region. And then what you get out of is a commodity matrix at a more disaggregate level.